Hello everyone, welcome to this introduction to exercise 26 from Astronomers as Observers and Experimenters, published by Kendall Hunt. I'm Professor Jeff Wilkerson at Luther College. Provide a little bit of an introduction to this exercise, which is the distribution of star clusters on the sky, on the celestial sphere, if you will. And so we'll look and see where these star clusters are on the celestial sphere. And there are a lot of different directions you could go with this exercise. And you could have different learning outcomes, different learning goals in mind for whatever you want to achieve with it. For me, this is an exercise that's more about understanding the galaxy than it is about understanding these objects. But we always start with a little bit of an introduction to these objects. Presumably, you've been introduced to these objects before you do this exercise. But there are two distinct kinds of star clusters. Open star clusters are these star clusters that tend to have a few hundred stars in them. They can have a lot less than that. They could have a dozen stars or fewer, or they could have up to a few thousand stars in them. And so they're not as compact, they're not as compressed, gravitationally compressed as globular star clusters. Globular star clusters will have a few 100,000 stars in them and be pretty densely packed and relatively far away from us compared to the open star clusters on average. And so they look centrally condensed. They look uniform across the face-off, and it's hard to see individual stars. So usually you see individual stars in open star clusters and not so much in globular star clusters. But we give you an example in the text of this exercise of photographs that we took with the equipment here at Luther College that show you that you can have very sparse globular star clusters that look a little bit more like open star clusters, and very dense open star clusters that look a little bit more like globular star clusters. So it's not always trivial to tell by appearance. Usually you can tell them apart. But one thing that's for sure true, and their ages are different. Typically, globular star clusters are uniformly old. The Milky Way's globular star clusters are uniformly old, and the open star clusters in the Milky Way are a wide range of ages. They could be very old or they could be quite young. And the reason for that is that if you make our galaxy, if you make a schematic of our galaxy that looks something like that, here's a tip. Sometimes if you were to make a schematic of the galaxy, the central bulge might actually be central. It might be located in the middle of the galaxy. So let's just make the disk a little bit bigger like that. I don't know. Anyway, if we're out here someplace, we look back toward the center of the galaxy. That's the central bulge. And we have this flat disk that we're living in. And it turns out that the globular star clusters are in a distribution around that central bulge. And the open star clusters are scattered along the disk of the galaxy like this. So they have very different distributions. Open star clusters, globular star clusters. So we can have open star clusters that are very close to us, but we have to look toward the center of the galaxy to see the globular star clusters. Now let's start with, we can think about a lot of different things we want to try to achieve with this exercise. Let's start with saying if we want to map the disk of the galaxy, we want to know the shape, the size, where the disk of the galaxy is in the sky. The open star clusters are going to do that pretty well for us. And we have there's so many things we can think about here. We are, for this exercise, just using the clusters, the star clusters that are in Charles Messier's catalog, famous catalog. From the late 18th century. So this 18th century catalog of interesting objects in the sky, I think he was making it for objects that weren't interesting, so that they weren't comets, they weren't luminae, well, fuzzies that might be confused for comets. But now we know these to be extraordinarily interesting things. And so these are Messier's observing from France. So not by any stretch are they all of the clusters that we know in the galaxy. For the open star clusters, that would be quite a challenge. For the open star clusters, you could go to a book like this one, great reference book on star clusters, and I recommend it highly, Star Clusters by Archinal and Hines. And so you go to a book and look at all of the open star clusters, and the project would get to be daunting fast if we wanted to plot all of these clusters. So we chose Messier's list largely because we had to make a restriction somehow. Messier's list is a relatively famous list, and they're relatively bright objects and interesting objects to look at. So if you wanted to go out and observe them, and by all means, I encourage you to do so, go out and observe them, then you could find these objects a little more easily than most of the objects that were in that textbook, that reference book that I just showed you. So so we picked Messier's objects for that. Now for the globular star clusters, it wouldn't be that daunting to do all of them that are known in the Milky Way. I forget the number, but it's something on the order of 200 is all of the globular clusters that are known in the Milky Way. And so we could have actually done all of the globular clusters. It still would have been fairly daunting to do 200 of these things. But if you did the Kuiper Belt object lab exercise, then you know that we do sometimes work with sets that are like this, and you can certainly do it. But anyway, we had to cut, and this is how we cut. And what I want you to think about, and we ask you questions in the exercise to think about this, given that cut, they're going to lead to some observational bias. And if you haven't watched the video on observational bias, go back and watch the video on observational bias. But you could, so think about how making the cut that we made to make this a doable, a tractable exercise, a thing that you could get done, how that might lead to observational bias and alter some of the measurements that you're making in this particular activity. So there's a learning goal, if you will, that's associated with this exercise, is to say, thinking about observational bias. Another goal for this exercise for me, whenever I work with students with this particular exercise, is thinking geometrically. And thinking geometrically that's a thread that just simply runs throughout the course. And particularly thinking three-dimensionally, geometrically, about how what you see turns into, or let's have the arrow of causality go the other direction. How does the distribution of matter turn into what you see? And so in this case, if you've got a thin disk, so suppose we're here. I should have had the colored chalk out. I'm not sure where it went. But suppose we're here. That's us right there. If we look this direction, or out of the board, or into the board, or anywhere in that circular disk, let's say, it doesn't have to be circular, but in that disk that's perpendicular to the board, we're going to see a lot of stars. We're going to see a lot of stuff and a lot of open star clusters. If we look up this way or down this way, we're looking through the thin part of this disk, we're not going to see very many objects. We're not going to see a lot of stuff from our galaxy, our Milky Way galaxy that we have right here. And so we see very few clusters this way. As we work around this direction, we see more and more and more clusters. As we see further and further and further down the disk, you can see that way. And so we see, if we plot these clusters, they're going to make a map of where the disk of the galaxy is largely. Now, there will be a few outliers. If you look this direction, you might see something that doesn't quite correspond with the main axis of this disk, the main direction of this disk. But that's what we want to do. We make a graph of declination versus right ascension and see what this looks like. If we don't see anything up this way, this way, this way, this way, we see everything this way. If we have to look this direction, 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 in order to see the stuff, we have a fairly narrow range of material, of direction, excuse me, fairly narrow range of direction where we're going to see a lot of material. In this case, a lot of open star clusters. So that's a narrow band on this declination versus right ascension graph. Now, because declination versus right ascension, those are terrestrial coordinates. Those are coordinates associated with the Earth that were projected onto our celestial sphere. That's not aligned with the galaxy in any way. It's not intended to be aligned with the galaxy. It's not a coordinate system associated with the galaxy. So that's going to look, a narrow band isn't going to necessarily be flat on a diagram like this. You're going to see it do something like that, and you'll see this narrow band start to emerge. And that's what you're going to look for. There you're mapping the disk of the galaxy. You're sort of understanding where to look. If you want to do a senior project, so you got a senior project coming up, and you want to study the disk of the galaxy, this is telling you where to look for the disk of the galaxy. Maybe you want to study star-forming regions, and star-forming regions exist in the disks of spiral galaxies. You better look here, don't look here. Okay, so this is giving you valuable information about how the geometry. So first of all, it's giving you information about the geometry of the galaxy. If you doubted that the Milky Way was a flattened disk, you should, that this component of the Milky Way was a flattened disk, you should have less doubt. You always have some doubt, please. Always retain a little bit of doubt. But you should have significantly less doubt after making this plot and seeing that relatively narrow band on this diagram to say, that's consistent with a flat disk that we're sitting inside. And so that's what the solar system looks like if you make the solar plot of objects in the solar system along here. Maybe a few outlier objects don't fall into the plane of the solar system, but they look like that, and you start to understand how we can build a geometry. We can understand the geometry of the galaxy. So that's the geometrical thinking that is important as a learning goal for this particular exercise that comes from making this graph. If you do the same thing for the globular clusters, okay, you make this same kind of graph for the globular clusters, then what you'll get for the globular clusters is something that's very different, okay? And I'm not going to draw that for you. I want you to go out and look at that. And that's one way to tell you the globular clusters and the open star clusters probably are different things because they have very different distributions. So just looking at their distributions tell you that there's something different about them. And so you'll see the distribution in space here. Another great way to look at the globular clusters is to make a graph, a histogram of their right ascension values. Okay, you could do it for their declination values too, and to see if that yielded anything interesting. I recommend you do it. Okay, I recommend you make these graphs by hand with the paper that's in the lab book, or do it with a computer. And doing it with a computer is great. But to make a histogram, what you do is you break this up into hours of right ascension, for example. Maybe you have to make a decision. When you make a histogram, you have to decide what your bin size is. What bin size makes the most sense to you? Maybe you want to split it up into half hour of right ascension, or a full hour of right ascension, or 2 hours of right ascension. But suppose you did 1 hour of right ascension. That's a decision you're making. We've harped on this before. We talk about that astronomers have to make decisions, and how they make decisions by and large determines how successful they're going to be with whatever it is they're trying to achieve here. So you're making a decision on how to bend the data. The good thing about a decision like this, you don't like the outcome, rebend it. You do like the outcome, rebend it. Try it different ways. But to say a bend would be 1 hour. So that could be 0 to 1 hour, 1 to 2 hours, 2 to 3 hours, and 3 to 4 hours, and so on, all the way out to 24 hours of right ascension. Now, if between 1 and 2 hours you had one globular cluster, you make a mark here at 1 and a mark here at 1, and you draw a flat line connecting them and vertical lines like that, and you're making a histogram. If between 2 and 3 you had 3, draw a line at 3 and 3, vertical line, horizontal line, and you have a histogram that maybe you've seen histograms before. And so you see, now suppose you have 2 between 3 and 4, you draw one at 2, and at 4 you draw it at 2 and make your horizontal line and your vertical line, and you see how we're starting to make a histogram. If that histogram is flat across here, there's going to be noise. There's going to be counting noise. Poisson statistics, you hear me say that a lot. You don't know what it is, don't worry about it. You're going to have counting statistics in here. But if it's consistent with more or less flat, there's no sort of clumping or trend or anything like that, then you can say they're at all hours of right ascension, much like you might see the open star clusters. But if instead it looks something like this when you do your histogram, number of clusters versus right ascension, if it looks like this, and there's maybe an outlier here or an outlier there, but most of them are clumped in this position right here, you can say, oh, there's a particular right ascension where we find the globular clusters, and this kind of histogram helps us see where that is. And this is so another learning outcome, despite one of the things we can get out of this lab, in addition to trying to understand the geometry of the galaxy and how the globular clusters and open star clusters might be different kinds of things, one of the outcomes that we could try to achieve is understanding how certain types of graphical analysis help us better understand our data set. And astronomers would use this technique a lot. And to say, making a histogram, I'm all about histograms. Okay, I really like to make histograms of all kinds of things. People who know me know that I tend to count the number of trick-or-treaters who come to my door. in every Halloween in 15-minute intervals, and then I make a histogram of the number of trick-or-treaters in half-an-hour intervals or 15-minute intervals or whatever we have right there that we've broken this down into, and I make a histogram like this where this is the number and that's the time that they arrived, and I can tell you then, I can go back 20 years and tell you by day of the week, are trick-or-treaters more likely to come earlier or later or whatever. And so this histogram goes a long ways to helping you understand that. So making histograms, practicing making those histograms helps you become a data analyst and thinking about how we're going to use that data analysis to understand something about our galaxy or something about the nature of these open star clusters or globular star clusters. Now, if you wanted to take this to a different level, if you wanted to do some statistical analysis with this, by all means, you can do that. And one of the things that we've asked you to do in here is to find the mean value to say, let's act like, this is what Harlow Shapley would have done. When trying to understand the nature of the galaxy, the size of the galaxy, is to say, let's say these things really are centered on the center of the galaxy. And if they are centered on the center of the galaxy, then the right ascension right here and the declination, the average right ascension and the average declination should give us the right ascension and the declination of the center of the galaxy. So let's find the mean right ascension and the mean declination of these globular star clusters and see how it corresponds with the known right ascension and the known declination of the center of the galaxy. Ask yourself if it makes sense given the uncertainty, or ask yourself about observational bias like we talked about earlier. So this is a good way to practice doing some of this statistical analysis. If you could take it even further, what I would do with a distribution like this, if I had a histogram like this, is I'd fit a Gaussian curve to it. And if you want to, if you're interested, I'm sure you are, if you're interested, there is a video out there of me doing exactly this in a program called Kaleidograph. So if you happen to be using a program called Kaleidograph to do fitting, and you want to get a little bit of a tutorial on how to make a histogram and fit a Gaussian curve to it, and use the mean and standard deviation of that Gaussian curve to understand the uncertainty, the standard error, and the uncertainty in there. Maybe we'll make a video here as I think about this, just talking about that kind of work. You're doing a little bit of statistics work if you want to learn statistics. If that's one of the things you want to learn as you're going through a course, you're going through learning about the universe, learn a little bit about statistics at the same time. Maybe we'll build a couple of videos out there about doing this kind of work. But for us here now, we can just measure the distributions of the open star clusters. They map the disk of the galaxy, the plane of the galaxy, measure the distribution of the globular star clusters, and we're going to say they're mapping to a certain degree the center of the galaxy, the central bulge of the galaxy, and to figure out what those distributions look like and what we can learn from those distributions. So it's a fun exercise to be able to do this with these, and if you want to, I encourage you to go get more data. If you want to do all of the globular star clusters, go find the data for all the globular star clusters. I'm sure you can find it online as well. And so use the data for all of the globular star clusters to do a better job of refining your measurements for this. Turn it into a project. Do it for 300 or 400 or 500 open star clusters, and sort of try to understand, can you measure the difference? That'd be an interesting question. Here's an interesting research question if you want to do this as a project. Can you, looking in different directions, how do the numbers of open star clusters vary? So if I look toward the center of the galaxy, how many open star clusters do I see in a given angular range, for example? If I look toward the anti-center of the galaxy, how many open star clusters do I see? And can I then tell that there's less material in the anti-center of the galaxy than there is in the center of the galaxy? This is not unlike, it's related to one of the projects that's in the back of the book where we use a website called WebDA, which is a great website. I encourage you to go out and look at it. If you want data on open star clusters, that's the place to get data on open star clusters. And so you can imagine turning this into a project to think about mapping. Can we see far enough? That's a way to ask that question. Can we see far enough into the disk through the disk of the galaxy to actually tell that there's more disk in this direction than there is in this direction or this direction or the direction into the board? I don't know whether we can or not. There's enough dust and gas in the disk of the galaxy. You run out of clusters because you just can't see that far into there. If you see the same in every direction, that's telling you there's enough dust and gas that you're not mapping very far into the galaxy. If you see more in this direction, that's telling you that you are mapping into it. You've learned something about our ability to measure in the galaxy. So anyway, there's a project if you want to take that on. Good luck with this exercise. Let me know if you have any questions with it. You can probably find me out there. It's a good one, and enjoy, everybody.